Yeah, good. Alright, is that plugged back in?
Yeah.
So yes.
Yes.
Okay, is it like on?
Yeah.
Oh, really? Cool. Okay. If it's, the pen. Okay. I had a piece of paper somewhere. Maybe I don't need it. There. Okay, here comes the coolest thing of all. What I now want to talk, what I'm going to prove is a famous result from the 18th century called Eulers' theorem. He has a billion of them. So, yeah. This is the theorem regarding the number of vertices, edges, and faces of a polyhedron. What is a polyhedron? It's like a shape from geometry. Can I get a formal definition of polyhedron? Can I get a simple definition of polyhedron, like simple from geometry?
Equilateral faces.
No, I'm just resorting to just being mean and pushy. That seems like a better.
Yeah, that's not very nice.
That's not. I know it's not nice. I don't care.
You're not nice.
I try to.
Isn't it?
I want to keep everyone awake. Being nice is my third on my list. What is a polyhedron? This is just like literally like a 7th grade geometry objective that you know what a polyhedron is. It's a shape, a 3D shape composed of polygons. Yeah, that's it. Not so hard. It's a shape whose sides are a bunch of polygons. Okay, so like not a sphere or like a cylinder, but shaped with such points. Okay, and for any polyhedron, there is a relationship between the vertices and edges of this polyhedron. And here is the relationship. Let me make sure I get this right. The number of vertices, no, the number of faces, yeah. So let F be the number of faces. Let V be the number of vertices, and let E be the number of edges. In any polyhedron, the number of faces is the number of vertices minus the number of edges plus 2. It's like amazing. Have you guys never heard of this before? It's like a famous, thing.
I think we have once.
You did this in pre-com?
Do we?
Oh, I'm sure you did this like in middle school, if ever. But it's also just like a. Okay, so for example, take this cube-looking thing. How many vertices?
8.
8. How many faces? 6. How many edges?
12. 10. 12.
Wait, I think I might have screwed this up then. Edges. Yeah, these are backwards. Edges minus vertices. Edges 12, vertices 8. Boom.
Oh wait, this one here.
Well, this sounds kind of fun.
Yeah, this is on the SAT.
Really?
Was it? How'd I pass?
I
don't remember this thing.
Okay, take a tetrahedron. How many vertices? How many?
4.
How many? Yeah. Then how many? First of all, how many faces?
4.
4 faces. How many edges? 6. How many vertices?
4. 30,000.
Okay, and this is true even with like really complicated, really complicated stuff. Okay, and maybe we should take a quick well, let's see. Should we prove this first, or should we first look at the regular polyhedron? Let's look at the regular polyhedron. Okay, this is actually kind of fun. Everyone take out a piece of paper if you don't have one out right now. We are going to practice planar embeddings of the regular polyhedron.
Oh my god.
What does it mean to be a regular polyhedron?
Ooh,
This is, for example, a dodecagon. Dodecahedron. This is a dodecahedron. What is a dodecahedron? It is one of the 5 regular Platonic solids. What makes it a regular, why is a platonic solid a platonic solid? Well, first of all, it's a polyhedron, so all of its faces are polygons. Second of all of its faces are congruent regular polygons. What's a regular polygon? A regular polygon is one with whose sides are all congruent and whose angles are all congruent. So this is a regular pentagon, and also all these pentagons are congruent to each other. And also, there are the same number of them meeting at each vertex. So this is a dodecahedron composed of some number. Is it 12? No, it's
Yeah.
10.
Dodeca is 12, right?
Yeah, dodeca is 12. Yep, 12 regular pentagons with 3 meeting per corner. Okay, good. We can play with that. I think I have more. This is the simplest platonic solid of all. It is a tetrahedron. A tetrahedron is composed of 4 equilateral triangles with 3 meeting at each vertex. That's pretty fun. This is an octahedron. An octahedron is also a platonic solid. It is composed of 8 equilateral triangles with 4 meeting at each vertex. And I also have a cube. What's a cube? Duh. It's a bunch of squares, 3 in particular meeting at each vertex. This is an icosahedron. An icosahedron is a platonic solid with, I believe it is 20 equilateral triangles with 5 meeting at each vertex. Okay, here's another icosahedron, here's another dodecahedron, here is, that's all I got. I probably have another cube in here. Okay, so I have 2 dodecahedra, I have 2 icosahedra, I have 1 octahedron, 1, okay, so, fact, the graphs of these, I can produce a so-called planar embedding of each of the 5, turn the camera, a planar embedding of the tetrahedron. And in fact, all of them. Okay, so what is the tetrahedron? The tetrahedron is here. What?
They narrowly embed the higher dimension platonic.
Okay. Okay. So here's the tetrahedron. What do I do with the tetrahedron? Take a face off. So mentally remove this face. Okay? Has everyone done it? Okay, and now take these 3 points and stretch them out and make the graph flat. What does it look like? Draw it. In other words, draw a 2-dimensional graph, a planar graph, which respects the various adjacency relationships between the vertices, but in which this face becomes just the outside region. Yep. This one is the easy one. Yep. If you take this and you think about what it looks like, there's these 3 points are like a triangle. 1, 2, 3. And then there's that point in the back, right? And that point in the back is connected to each of those. You guys following this? Say yes.
Yes.
Okay, and then the outside face, so this back face becomes this one, that back face becomes that one, the bottom face becomes this one, and the face which I told you to remove just becomes the entire outer region. So this is a planar embedding of the tetrahedron in the sense that the tetrahedron has 4 vertices, so does this graph. The tetrahedron has 6 edges, so does the graph. The tetrahedron has 4 faces. The graph has 4 regions, including the outer region being rough. Follow? Say follow. Okay, good. Next, what's the next easiest one? How about cube? How do we do a cube? Same thing. You want to try it first, or you want me to do it for you? Try it, just try to raise me. What I will now do is I will take the cube, I will take the outer face.
Like a square with a
Yup, why don't you draw it?
square.
Draw it, right now, draw it, Kathleen. Yeah, Kathleen, still in high school, do what I say. Take out a piece of paper, draw the thing, good. Okay, so I have a cube, take this face off, remove it, throw it away. It is going to become, or if you'd like, think about it stretching out to be infinity, that's what's going on here. And draw the planar embedding of the cube.
But then it says
So if you think about these 4 points as being like stretched out, then in the back there are the 4 points, right? And the back 4 points form a square, and then they're connected to each of these. You guys find this easy or hard? I think it's hard. These two are easy, so I'm doing the easy ones for you. How many faces does the cube have? 1, 2, 3, 4, 5, 6. Okay, go. Do the rest. Draw the planar embedding of the octahedron, draw the planar embedding of the icosahedron, and then planar embedding of the dodecahedron.
not that bad.
If you want to borrow one, come grab one, they're over here.
Octahedron is the one with 8 triangles.
No, it's not. It's a square.
I think I know what it looks like, but I'm like, not too certain.
Hi, Yoni.
Hi, Yoni, the camera loves you.
Yoni, you're so popular. Teach me the secrets to your success.
Show me the shape.
She's just staring at this guy. I'm gonna touch this.
I feel like the icosahedron is hard. I found this to be really hard the first year I did it, but then we got
I
better.
don't know if this is what it looks like, but I think
I'm trying to figure out what this is supposed to look like. Josephine, may I see?
this is right.
Did you get you got the octa, right?
This is not planar.
Definitely not good.
I don't know if you can do this. You remove one.
This is really weird.
How many sides are there?
Yeah.
1, 2, 3, 4, 5, 6.
Yeah. Maybe it just looks, your picture looks really ugly. No, it's not planar. It's gotta be planar. I don't think so. Because the octahedron has 6 vertices only, right?
2, 3, 4, 5, 6.
No,
Yeah, I don't have 6.
I have some. Okay.
The octahedron has only 6
I
vertices.
think you have to like
And how many
stare at
edges?
one face.
4, 5, 6, 12 edges.
I know you have to stare at her, but
I don't know what I'm doing, guys.
That totally works.
Oh, you do.
Isn't
What's
this
up?
the dodecahedron?
Something like that, yeah.
I'm done.
how'd you do it?
It's just the thing again. You're just stuck with pentagon inside a pentagon inside a pentagon.
Okay. So yeah, you take a thing, you imagine it gone,
Why is it 2? Why is it? Oh wait, no, this is
and then,
I see the other ones.
yeah. Here, I think the pretty picture of this is it's like a big triangle, and then there's like a, upside down over there. And then, each one's connected to 4 things. So it's like a Zelda Triforce thing.
This is all the Triforce?
Kind of. I think that's the octahedron, right? Every vertex has degree 4. There are 8 faces. 1, 2, 3, 4, 5, 6, 7. Your picture might look like that, but it helps if you're holding the thing. I mean, Christine taught me it, but if you hold it, take a face off, and then let your brain go. Take the 3 that are going to stretch out to infinity, or that are. Take the face. The face that you remove becomes outside, right? Becomes the outside. So then these 3 points go all the way to the outside.
Yeah.
I drew my thing, but it doesn't have all the.
Wait, hold on.
I only had 6 ones. Yeah.
Okay, those of you at home, try this.
Try it.
How was physics?
I don't know what I'm doing.
Music theory.
It took a long time. Sat in the room for like 2 hours waiting for sex.
Good. We learned lots of math today.
Yeah. Are you going
Okay, so 4, 5, 6.
Yeah, it's really hard. You need to hold it in your hand. So watch, Gabe's doing it. So So you take, usually you take the thing, right? Take this
You
face.
only have 6 on each
Decide that this is the face of the
6 regions?
Yeah. I think it's that you
Now.
have to like.
You hold it up like a lock. Okay. And now, these 5 points, stretch them out to be flatten the entire thing out. So what you end up with is a giant pentagon on the outside and like an inverted pentagon in the middle, which is like the back. So take, it's really hard. I think it's good. You take these 5 points, 1, 2, 3, 4, 5. Take the space, it's gone. Okay? And now what you want to do is, stretching is allowed. You want to flatten this whole thing. So what you end up with is a giant pentagon. This is the way to do it properly. You can also just start drawing some random crap and hope for the best. But then, as you look deeply into that pentagon, you see that there's another pentagon in the back. How you guys doing with this? Some people do better at this task than others, based on your skills with visualization and like art and stuff.
I was just figuring out how many things go into a corner.
And then, by the way, every vertex has degree 3.
How do you do the octahedron?
And then, so that is connected to like one more thing. And that one more thing is connected to
18 faces, right? 20.
2 other things, which are connected to those things.
That is definitely 20.
Okay, I know. Okay, bro.
Keep
I
drawing.
got it, bro.
I don't understand it.
I'm not getting this.
So that's kind of what you
like this,
do.
triangle like that. Right? I feel like we should. There's also like an height there. This is like whether you have to.
Thing we learned in
Okay, so if you had to take like the back of it and just like expand it,
Now I'm having trouble.
I'll make it bigger.
right? You just like stretch it out.
Okay.
So like,
it's probably different for.
So it's like you rip this back off and then you go.
and then you just like pull it out, right?
Alright.
And so you have like this triangle. Like there's a triangle.
Okay,
We
wait.
did this.
So you have a downwards triangle. I got that. Okay. And then you pull this up.
This doesn't work.
And then this connects down.
Take this.
Whoa, good job.
Kind of like pulls out.
Okay, wait. And then you put this down here. So this connects down.
Take this and try to like pull it out and like.
But then this.
Looks like
So you have these triangles. They kind of like pull up. The middle is a square.
Wait, no.
So you have this triangle. You have these. Right? It's adjacent to two triangles. You see those? And that's those. Yeah. Okay. That's triangle. Those are back triangles. Right? And then you just and you like.
it's a problem for you, I guess. Did you do that?
So let's see, did I do that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10,
Oh, and
11,
then here
12.
there's still one.
Okay, then the octahedrons like an iron.
Okay, well,
I got it!
Hey.
Oh my god.
Yeah. Yeah, you take, so you remove 1 and then you take those 3 and you go all the way out.
Yeah, I saw that.
What does it look like?
Yeah, it looks like that.
That's great.
1, 2,
Then inside is a thingy. But then there's like a lot more going on. Wait, still rotate.
I have much.
Yeah, 10.
Wait, how many verbs do you have?
12?
20, right? No, 12. No, you're right. 12.
Well, 20
Yeah,
faces
we're good.
with 12 verses.
Yeah.
No, I'm talking about like this. Where it's like they're like triangles.
Okay.
Yeah, that's what I usually do.
And you just like add the other two triangles.
I think mine works.
I just have to
Five.
like it's just drawing circles around to connect the end parts at the bottom.
Well, same.
Yeah, I got it. Okay, cool.
Josephine,
that
so
mine-
pro.
It's like messed up.
You kind of keep doing it, but then it gets hard. I feel like there's a little more systematic. Well, anyway, I guess it's okay. Good. All right, how are we feeling about all this?
Not very confident.
Good. Good. That means there's some learning in your future. All right. I would like to prove Euler's theorem. I got 9 minutes. It seems like a perfect amount of time.
How are you doing this? I do not have a neck. Some people have an neck to this, and I
Oh, someone turn the camera already? Thank you very much. Okay. Euler's theorem says is really a theorem about simple connected planar graphs. So Euler's formula, actually that's what people call it. Euler's formula says let G be a connected simple planar graph. Okay. With epsilon edges, and n vertices. Let rho be the number of regions in a planar embedding, including the region on the outside. So let rho be the number of regions, including the outside region. Number of regions in a planar embedding, including the outside region. I don't feel like writing that. So claim rho is epsilon minus n plus 2. Alright, so traditionally Euler's formula is thought of as a formula about polyhedra, but if we take any polyhedron and remove one of the faces, we can stretch it out so that it becomes a simple planar graph. Do you believe it? Yeah. Therefore, it is more smooth to think of it as a theorem about planar graphs. By the way, just a quick shout out. There's this book called. There's this book. If you took logic this year and you're like super interested in following up on that class with an extremely hard math textbook, pretty much just Brian Mars. But anyone else, there's a book, it is called Proofs and Refutations. Does anyone know Jonah Chazan, who graduated like 2 years ago? Remember that guy? His dad is a professor at the University of Maryland, and he reads this book with his people that he's training to be high school math teachers. It's an awesome, awesome, awesome book. The entire book is 200 pages long. It is written in the form of a Socratic dialogue between a whole bunch of math students, all proving Euler's formula again and again and again and again and again and again and again. It's like really, really interesting and really hard, really cool. Okay, do I have time to prove this theorem? I do. Here's what we do. We say, well, the graph is simple. It is also connected. Did I say connected? It is connected. Well, what we're going to do, anyone, is we are going to have a bunch of edges, and we are going to make the graph by adding one edge at a time. And it is possible to add one edge at a time in such a way that each of the subgraphs is connected. In other words, and this is just true about any connected graph, if you have a connected graph, take this graph, it's connected. What is one way in which I could make this graph in a step-by-step way? Well, I could, if I wanted to be weird, I could start with this vertex, and then I could do this one. But like, don't do that. Like, do it in such a way that you add them in some okay, so that's good. So add these things one at a time. All right, well, claim. What happens when you have one edge? Well, if you have only one edge, So call this E1, and this graph is G1. What is G1? G1 is step 1 of an algorithm, which it's not really an algorithm. It's just step 1 of the process in which you're going to slowly build up your graph. So G1 has only one edge in it. This is V1 and this is V2. Okay, at the moment, let's keep track of how many regions do we have. How many regions do we have? One region, that's just the outside. How many edges do we have? One. How many vertices do we have? Two. So is it true that 1 equals 1 minus 2 plus 2? Okay, so the theorem holds when there is simply one edge in the graph. Okay, now let's add an edge, but we're going to add an edge in such a way that the graph stays connected, right? So here is V1, here is V2, and if I'm adding an edge, well, I have to add the edge to either V1 or V2. So we'll call that edge 1 and edge 2. I'll just add it here. Call that V3. Okay, now how many regions do I have? Still 1. How many edges do I have? 2. How many vertices do I have? 3. Well, is it clear that all I did was add 1 to the number of edges and 1 to the number of vertices? So this is still, or you can just calculate it, this is still true. Or this formula still holds. Say yes.
Yeah.
Okay, so those are like the two base cases. So now we do like the inductive step. Can you turn the camera to make sure I'm in frame? The inductive step is to say, okay, I have some subgraph. So, so there's some subgraph that looks like, I don't know. So, and then we're just gonna do dots, because there's a bunch of crap going on. All right, and what I'm doing is, at every step, I add another edge, okay? Well, if I add an edge, there are only two possible ways to add an edge. I can either add an edge in a way in which I introduce a new vertex, or I can add an edge in a way in which I do not introduce a new vertex. If I introduce a new vertex, in purple, I will draw, so this is supposed to be a picture of, GK minus 1, and now I'm about to make the graph GK. How do I make the graph GK? By introducing a vertex which attaches to one of the like existing infrastructure. Okay, well, what effect did I just have on rho, epsilon, and n? What is the, let's say that we had, so we had like rho k minus 1, we had epsilon k minus 1, and we had n k minus 1. Do you guys understand what that means? There's the number of regions, edges, and vertices, respectively, in the previous graph, because we're building these edge by edge. Well, now, what is rho k? How many new regions have I created? None. So rho k is equal to rho k minus 1 in this case. All right. How many new edges have I created? 1. So the new number of edges is that plus 1. How many new vertices are there? 1. So the number of vertices in the kth buildup is just that plus 1. So have I changed the value of that formula at all? No, I have not. Okay, and the last case to consider is the case in which here is my graph of gk minus 1 now. So this is gk minus 1. What's the other way in which I can add an edge? I can connect two vertices that already exist. Well, if I connect, so now it's possible that in the kth step of my process, by adding a new edge every single time, it's possible that what I did was to create a new, is to add an edge between two vertices that already exist. Okay, well now if I had rho k minus 1, epsilon k minus 1, and n k minus 1, what is the value of rho sub k now? I add a region, for sure, right? Because when I connect to, on the assumption that the graph is already connected, when I add an edge between two vertices, I create now like a cycle, right? I have to create a cycle because the graph is connected. And now what are the number of edges I have? one more. How many vertices do I have? Same, right? Because I didn't add a vertex, but I did add an edge and I did add a region. Okay, so what happens to the value of, the simplest way to do it is to say, to take rho minus epsilon plus n, and to say that this has to equal 2, always, right? This is the theorem. But that's not how people normally write it. Well, over here I add one edge and one vertex. So that's canceled out. Here I add one region and one edge. So those two are canceled out also. So basically, in every single, I start with a graph for which this relationship holds. And then when I have two edges, this relationship holds. And every time I add an edge in a systematic way, I argue that this relationship holds. Therefore, the overall graph, when I finish, this relationship holds. Follow? Okay, that is Euler's formula. I was going to do one more thing, but I guess I'll do it next class, which is to prove that there are only 5 Platonic solids. It actually only takes like 5 or 10 minutes, but it's a cool graph theory proof of it. All right, you have some homework. What's up? There's a traditional geometry proof which is that one. Yep. But there is a sort of a more rigorous graph theory proof. That's based on Euler's formula. Okay, good. Bye, all you people at home. Hope you did well on your physics test, and you will have all surely watched this 2-hour video. Class, say hi.
Hello. Are you saying bye?
Say bye, I mean. Okay, seniors, get out of here.